Greetings, everyone. Welcome to the talk on learning from Haskell. My name is Venkat Subramaniam. Thank you so much for joining. Hope you're all staying safe and doing well. Well, we're going to talk about learning from Haskell. As the kind of title alludes to, we're not going to learn Haskell, but I'm going to share with you some of the lessons I've learned from learning Haskell itself. I'll talk a little bit about why bother learning something maybe so different from what I normally do, and what are some of the benefits I've derived over the years since that particular opportunity to learn. And that's what I want to focus on today. Well, one of the things that I really enjoy doing over the past few years is to learn different languages. Just to kind of give you a background, I started programming, maybe about 30 plus years ago, and I was predominantly programming in C++. That was the only language I was programming in for a long time. When I started learning yet another language, it was an eye-opening experience because it really gave me opportunity to think very differently than what I was used to. Today, I program in about 15 different languages. What I'm saying in so many words is I'm not good in any one of them, but I love the opportunity to learn and apply them in languages I program with. Well, most of us program in mainstream languages, and I would say the world today is ruled by a handful of languages predominantly. We could say C++, Java, C#, Python, maybe Ruby, and maybe a few other languages that are the mainstream languages. Of course, we have languages like Scala and Kotlin and Groovy, and of course, Clojure, and other languages, JavaScript, how not to mention it, right? So there are maybe maybe less than a few languages that really are predominant. Even though we program in those mainstream languages, learning a different language is a very useful experience. Goes back to what pragmatic programmers recommended, is to expand our knowledge portfolio and to learn a different language every single year. Well, part of the reason for that is language design is program design. It turns out when we are getting exposed to a language, we first get excited about the syntax of the language. Then we get used to the semantics of the language. But as it turns out, one of the most important things that we get from a language is the design capabilities the language allows. And it so turns out, if we program in one or a very select few languages, without knowing, we are limited to the capabilities those languages offer, and our brain kind of settles down on certain design options. However, that actually unfortunately gives us the power, but also is a limitation, not just for design, but on our thinking. This goes to software work hypothesis, which is a controversial one on natural languages. Well, a lot of us speak multiple natural languages, but a few select population only speaks one language predominantly. The Saffir-Whorf hypothesis says that people who speak multiple languages think differently and maybe even broadly than people who only speak one language predominantly. Now, this is kind of strange because, I used to think that whatever I think I express in the language I speak. The hypothesis says the opposite. It says the languages I speak influence my thinking. Well, I'm not a natural language expert at all. In fact, I wouldn't call myself expert for anything, but I do have experience with different programming languages. And I can definitely tell you, when I started learning multiple different languages, it fundamentally changed the way I design software, even in the languages I predominantly use, even though the learnings came from other languages into it. I'll share with you one experience I had. I was developing an application for an organization using C#, and as I was pairing with the developer, I said, hey, why don't we try something I've not tried in C#? And we immediately tried a little different way of writing code. All the tests actually passed, and we both were looking at the code and saying, oh my gosh, that's a lot different from what we do normally in C#. At the same time, the team leader came around, took a look at what we were doing, and gave me a little pat on the back and said, hey, are you trying to write Ruby in C#? Which is exactly what I was doing. I was applying a design concept that I was familiar with in Ruby, and I was applying that in C# at that moment, for example. Similarly, I've tried various different things from other languages into Java, for example, and so on. So this gives us new and different renewed design ideas when we can bring ideas from other languages into the mainstream language we program in. It also reduces the time we need to learn new concepts as the language we are using evolves as well. For example, first I came across the yield keyword in Ruby decades ago. Then I started seeing the yield keyword in languages like C Sharp and JavaScript, and more recently in Java as well. Well, exposing to these ideas really helps us to, learn very quickly. I'm not asking the question, what is yield? Often I ask the question, how is it different from what I already know? And that really accelerates the learning as well. So in general, I like to go off and learn something completely different. For example, I'll be absolutely honest and admit to you, I actually have learning disability. I cannot really learn quickly. However, if you ask me how much time I took to learn Groovy, I would say a couple of days. What about Scala? Oh, maybe about a few more days than that. But you say, how come you can learn things so quickly? Well, I learned Groovy after learning and programming in Ruby for a while. I learned Scala after programming in Erlang for a while. I had no reason to really use Erlang, but I was fascinated by the language. And I realized that Scala has a lot of concepts from languages like Erlang, even though Erlang is dynamically typed and Scala is statically typed. But that really accelerates the learning because you're exposed to the concepts already in multiple places. And that really is one of the reasons I like to learn different things, is that it reduces the learning curve for me in the long run, keeps the mental muscle active, if you will. But what I'm going to share with you in the next about 40 plus minutes is my experience learning Haskell and how we can apply that in whatever we do. Oh, best time to ask questions or make comments is anytime you have questions or comments, please post them on the chat and I'll be delighted to listen to your thoughts on the chat and respond right away. So let's get going. Well, I want to talk about my experience learning Haskell, but I realized that one of the most biggest enemies we have is our comfort zone. The more comfortable we get doing things, the less we are going to be willing to do something different. And in fact, the unfamiliarity often makes it harder for us to learn things. I would say the unfamiliarity is what humans definitely dislike. We oppose with vengeance what we are unfamiliar with oftentimes. So it's really important to get uncomfortable and then keep looking at unfamiliar things continuously. That helps us a great deal. But I have to admit, I failed really 3 times to learn Haskell. People kept telling me Haskell was a great language. I really wanted to learn it. And my first attempt to learn it was a disaster. I started learning it. The syntax put me off. The complexities put me off. And I said, maybe that's not for me. And about a year or so later, I said to myself, no, I really want to learn it. And I took it upon a second time and I failed at it. And about the 3rd time, I said to myself, no, I really want to learn this language. And I went full force with it, started playing with it incrementally. But one of my aha moments was about the 3rd time I started learning, I decided not to follow a lot of examples and completely ignore the type information and start writing code. And when I started doing it, it's almost as if Haskell was sitting there and looking at me and saying, hey, kid, welcome to the club. You finally understood type inference. That was an eye-opener for me because I was getting bogged down by specifying type information even before I started writing code. And Haskell said, you don't have to do that. I can figure out what the type is. Why are you wasting your time and effort? And that was a learning moment for me. And of course, it became a lot easier for me to understand Haskell since then. And of course, to learn it as well. And Haskell is one of the most statically typed languages over there. And also out there is one of the most strictly functional programming languages. So be it you are interested in static typing or you're interested in functional programming or both, we can learn from the language and we can apply it to mainstream languages. I'm going to assume that most of the audience here are familiar with and are programming with language like Java, but I'm going to relate back to Java and a few other languages as we go through and look at some of the things we can apply from Haskell into those languages as well. Not only that, you may be a language designer, maybe today or later, you might be a library designer, an API designer, or an application programmer. you can apply some of these ideas into your own code and your own design in a number of ways. That's what I want to focus on. So what are some of the lessons that I want to share with you that I took for myself from learning Haskell? The first is that static typing is very valuable, but get comfortable using type inference. Now, I do have to admit, I came from the background of language like C++, and you need to realize that static typing is more of a spectrum than an absolute value. So if you draw a line of static typing, you might put C# on very far end, pardon me, C++ on a very far end, and moving gradually towards Java. And then on the very far other end, you may put Haskell. It is very much of a disservice to say that Haskell is statically typed like Java or Haskell is statically typed like C++. That's a very unfair comparison, if you will. For example, if you look at static typing in C++ or in Java, we predominantly specify the type information over and over and over quite often. Let's take a look at an example here in Java just to illustrate the point, and then we'll look at some Haskell code to learn how we could do this differently. For example, you may say public static, let's say int add, and I'm going to add a and add a b as a value, and I might, of course, return from this an a plus b. But notice how we specified int 3 times already before going any further. Similarly, you could say result is equal to, and you could call an add with the 1 and 2, and you could output the result in the very end of this, like so. This is, of course, Java code. And when you run it, it produces a result of 3. But again, notice this is a statically typed language, but we spend time saying what the type really is. I'm going to make the claim the more statically typed the language is, the less you type with your fingers all the type information. So more typing is less physical typing, less typing or weak typing or less capability is more typing with the fingers. So I would say static typing to me is where the language is smart enough to determine the type and verify it at compile time, but not as much by re-saying this over and over and over. Let's look at an example in Haskell just to get a feel for what it would look like. So I'm going to say add over here, and I'm going to say add AB is equal to A plus B. And I'm going to go ahead and put a main is equal to, let's go ahead and say in this case, a print, and I'm going to put a result here where I'm going to say the result I'm going to bring in is going to be, oh, let me see what I just did there. So it got excited about what I was typing there. So let's try this one more time. So in this case, as you can see, I've written a function here called add function. I'm going to put a result in here, as you can see, and I'm going to say that let result is equal to add 1 and 2. So as you can see in this particular example, the result is a 3, as you can see. However, notice we did not say any type whatsoever. If I really wanted to, I could say add is a function that takes one integer followed by another integer and returns a response of an integer as well. As you can see, I did not have to type that line, but I can if I wanted to. This is specifying the type information. This line here is equivalent to we specifying that int and that int and that int. So 1, 2, and 3 is specified here as 1, 2, and 3 right there. But as you know, right now, that is optional. You didn't have to specify. But make no mistake, this is statically typed. So if I were to go back here and make a mistake sending a string here, notice we get an error saying, hey, you cannot pass a string because a number is expected. In fact, let's go a little further with this just to entertain this thought, if you will. I'm going to bring in the REPL for Haskell right here. And I'm going to say, oh, let's go ahead and ask it to display the type information. Add AB is equal to A plus B. And notice right off the bat, it inferred the type as num to say that it's a number, which is a super type of integer and fractional and so on. So you can see the type inference actively at work. But how did it know to infer the type? Well, the compiler says, hey, look, I found a plus being used. What in the world supports a plus on two values? And it realizes that the type that actually supports a plus in the system known to it is num. So it determines that it actually is. But going a little further with this, if you will, notice that in this particular example, I did not say what the type of result is. I simply said let. Well, we can apply some of these concepts, as you know, in Java as well today, not to that extent, but to a limited extent. You could say, for example, a var result is equal to add 1 and 2. Now, keep in mind, there's no concept of a var type in Java. Sometimes people mistakenly say it, but var is simply like a let in the case of Haskell. You are telling the compiler, hey, go infer the type for me, rather than me having to type that information. You can figure it out. There is no reason to do it. Now, if you are looking at a language like Java, really important to get comfortable with type inference. I know if we have been programming predominantly in a language like Java, it's incredibly hard to accept it. But over time, as you program in multiple languages, that's one thing you would really be excited about, is to come in terms with type inference and start really benefiting from it. So if you're really apprehensive to using type inference in Java, keep in mind that might really be not you, but unfortunately your familiarity and the comfort that you have developed with Java that makes your mind really feel that way. But with a little bit of experience, you might actually become a lot more willing to accept type inference, or maybe your team for that matter, if you're already on board on that. Now, with that said, one other thing that's really exciting is polymorphic type. Again, it's really hard to compare this with templates in C++ or generics in Java, because polymorphic types are brilliant in the case of Haskell. Let's take a look at what that really means with a little example again. Let's bring up the REPL for Haskell one more time and look at it. So here I'm going to say, let's again set the type information so it displays the type details for us. I'm going to say echo A equal to A. Notice it says that echo is a function which actually takes a type P and returns a type P. Well, earlier you saw num with an uppercase N. Convention is types start with an uppercase, but a lowercase represents a generic type, if you will. So in this case, if I say echo of 1, notice it inferred the type of P to be a num, as you can see, pretty smartly, as you can see here. On the other hand, echo hello, on the other hand, notice the type of P now is actually a character collection, as you can see, as opposed to being a num, as you can see in this particular case. So you can see the language being active in polymorphic type, knowing that we couldn't really nail this to a particular type, as opposed to add AB, where it was able to determine that A and B really are num. In this case, it decided it's going to be a polymorphic type, as you can see, because it cannot really determine the type based on the context. It could apply for just about any type, if you will, and it was able to make that decision for us, as you can see, in that particular case. So that's basically the first learning lesson for me, is that type safety is great, type checking is great, static typing is very valuable, but I want it to get out of the way. As I program, I want static typing to be in the background, verifying at compile time and giving me early feedback warnings and errors, but I don't want it to burden me into specifying the type. So I'm a huge fan of type inference. I use that in Java where it makes sense and where it's possible. I make use of it extensively in languages like Scala and Kotlin. And of course, I rely on it very heavily when I use Haskell as well. So it's something that we can benefit from and get comfortable. So lesson number one is static typing is very valuable, but please get comfortable with type inference. That's where the real value is for us. We can write less ceremonious code, but give good descriptive names for variables. If we can give domain-specific name for variables, the type information becomes less important in code, at least in the internal part of the code, even though you may want to specify the type when you have, releasing APIs. So put the type information on the boundaries for internal code, rely upon type inference as much as you can. And that's a practice I've followed in multiple languages over the years, thanks to the lessons of type inference from languages like Haskell. Well, the next thing I want to talk about here is that the compiler should work for us and not the other way around. So you want the compiler to be really smart, so it removes the burden on us and the ceremony on us, so we can work with things in a much more effective way without having to write code over and over and over just to satisfy the compiler, if you will. Let's again take an example in Java just to illustrate this point and how we can benefit from some of the things in other languages as well. So let's say for a minute, I want to create a list of integer. And in this case, I'm going to say numbers is equal to new array list. Okay, we started with an array list. Then I say numbers dot add, and I'm going to add a value of 1, maybe a value of 2 and a 3. We can add that right there, as you can see. So I've added the value of 1, 2, and 3, and I want to output the numbers given to us. Now, as you can see in this case, the result of this operation is 1, 2, and 3, but that's a lot of verbosity in the code, as you can see here in Java. But do we have to really work this hard in general, or can our lives be a little bit easier is the question I want to start with. Well, once again, let's take a look at what we can do here in the case of Haskell. Well, I can say let numbers 1 is equal to, and I can say 1, 2, and 3, much like what we would want to do in other languages, but with a lot less difficulty here, as you can see. So this prints the values 1, 2, and 3, as you can see. Well, as you can see, it did not take a lot of effort at all to create that collection of data. Well, thankfully, we can do something similar to that here in Java today, thanks to some recent developments. So for example, you can say a list of integer, we'll call it numbers 2 is equal to list of and 1, 2, and 3. Almost like in Haskell, isn't it? And we can print out numbers 2 right there. And when we run the code, you can see it's the same value, but with a lot less effort. Now, clearly, as you know, this created a collection of mutable list of values, whereas this is immutable, which is probably not a bad idea. It's probably a good thing. So there are some differences between the two, but from the conciseness point of view, I would rather write this code where possible rather than writing that code. And even if I do want a mutable collection, if you will, I prefer doing array list like so, and creating the array list like that. So now I have the best of both worlds, conciseness and a mutable collection as well. As you can see, obviously here, numbers 2.add 4, and I'm able to mutate that and add a value to it if I really wanted to. So I would rather write a concise code rather than a verbose code like so where possible. And that really is a lesson we can take in terms of look out for conciseness as much as you can. But going back to Haskell again, we can say, hey, why don't you create a 1 to 10 for me like that? And I want to go ahead and print it out right there. We can say print numbers 2 right there, and we can display the collection of values, which is a range of values we're going to get from numbers 2 in this case. So I said let numbers 2 is equal to numbers 2 right there. Let's make that fixed. And you can see in this case, when I run the code, it prints all those values in the collection. Well, what if we can try something like that? Well, here's an example from Kotlin, if you will, just to illustrate that point, and an example from Groovy maybe we can provide as well. So let me actually give you a Groovy example first of all. So I'm going to say define numbers is equal to, let's say 1 to 10. I want to print line numbers like so. So this is a Groovy code which gives me a range object like so. But again, in this case, I can say print line and numbers. Let's say I want to get the third element in the collection. And you can see in here, we are able to output the value of 4. So that's a Groovy example, if you will, that shows how we can do that collection of data. You can have a range in the case of Groovy. Likewise, in the case of Kotlin, I can say numbers is equal to 1 to 10, for example, and print line numbers, and that's a collection of numbers from Kotlin, as you can see. But we can take that a little bit further in the case of Kotlin, again, from lessons from languages like Haskell, if you will. So for example, back here in Haskell, what if I really wanted to, maybe go ahead and provide a set of values that are in the collection, but a couple of interesting things we can do. Well, first of all, here's an interesting part about Haskell, what it can do. Number 3 is equal to 1 comma 4 dot dot 10. Well, a little bit intuitive, but it depends on how we infer this. But what in the world is numbers 3? Well, as it turns out, Haskell is saying you want 1, you want to skip 2 and 3 and get 4, but you want to keep going. So I'll skip 5 and 6 and give you 7. So as a result, it becomes 1, 4, 7, and 10. As you can see, you can look at the fluency and the capability in here. Pretty fancy, isn't it? Similarly, you can go ahead and print out, in this case, a head numbers 1, if you will. And I want to print the values. Let's take numbers 2 rather. And you can see in this case, the head is going to be the very first value in the collection. And you can see a value of 1 being printed. However, you can also ask for a tail. I often say a small head and a big tail, and some languages call it as a rest rather than tail. And similarly, you can call a unit, which is everything but the last element. So you see the 10 is missing in the output. And similarly, you could also say a last, only to get the last element rather than all the other elements. And you can see some of these notions in here. Likewise, if you will, back here in the case of Kotlin, you could easily do a dot first, if you will, to get the first value in the collection. And that gives you the value of 1, as you can see in here in the output. Or you can also do a last, if you will, to get the last element in the collection. And as you can see in this case, the value of 10 is printed out as well, as you see in the output. So that's an example of how you can use some of these fluent pieces of code to easily access things. So low ceremony, and you can actually focus on getting your work done rather than having to write a lot of verbose code. So compilers can become smarter to really make it convenient on us. Similarly, when we design our own libraries, we can think of making things really easier for us as well. That could be a nice opportunity for us to use. Well, that said, I do have to say there is one thing that I've fallen in love with quite often in multiple languages is this concept of tuples. You have tuples available in many languages today. For example, Haskell has tuples, and so does Scala and C# and various other languages. In the case of Kotlin, you have a pair and a triple. So you have a tuple. Tuple doesn't always mean 2. So tuple is not a couple, but even though it sounds very similar to couple and tuple. So tuples are really, one of the beautiful things about tuples is they are really concise, but more important, they are immutable as well. So that becomes a nice way for us to create a small collection of data which are of fixed size and becomes easier to access it, if you will. Let's take a look at an example of a tuple, and then we'll move forward and see how we can use that in other languages other than Haskell in here. So let's say for a minute, I want to say let names is equal to, let's bring our friendly, well, our not so friendly tuples, Tom and Jerry, let's say. So here is Tom and here is Jerry that I brought in, the famous pair of characters, if you will. And when I print it, you can see Tom and Jerry. Well, that reminds me of an experience I had. This is a true story. I once called a support line and I seriously, sincerely asked, may I speak to Tom, please? And the person who answered the phone said, Tom is out to lunch. This is Jerry. Can I help you? Seriously, I hung up. This got to be a conspiracy, right? Well, anyway, we have a tuple called Tom and Jerry right here, but I want to get the first element from this collection. How do I do that? Well, it turns out I can simply say first on the name like so, and you can see I can get Tom alone. Or likewise, I can go back here to this example and I can say in this case, maybe a second. And in this case, I want to get a second element, which is the name Jerry, as you can see. So this is an example of using a tuple. Now, like I said, tuples are immutable. Well, in the case of Haskell, almost everything is immutable. Well, in the case of language like Kotlin, we can benefit from this as well quite nicely, if you will. So for example, I can say names is equal to, and you can see, say Tom to Jerry. Well, the to is an extension function in Kotlin, and the to function is on any, and it returns a pair as a response, if you will. Just to emphasize this point right here, just so you can really actually see it, if I say print out names like so, you can see the names is Tom and Jerry as a pair, as you would expect from the output. On the other hand, though, just to emphasize, if I go back to the code, and if I were to try to assign the type to be a string, just to illustrate the point, look at the error message you're going to get right now. And the error message tells us that we are expecting a pair of string, not a string. So the to function was returning a pair just to illustrate the point. So what you're getting here is a pair of, let's say, a string, comma string. That's basically what the type returned here is. And we were using type inference like so earlier on. And you can see when I write that code, you can see from the output right there, it's quite happy with it because the type is a pair that we were returning. So now that we have a pair of objects being given to us, what I can then do is to get the values out of the pair like so. For example, I could say name start first and access the first element in this collection, or the name start second and access the second element in this pair or tuple as well. I can get that very nicely. But of course, as we know, Kotlin is not a functional programming language. It's a hybrid programming language. So what if I say name start first is equal to, maybe, Joe in here, or Joy for that matter. And if I were to assign that, well, you cannot mutate a value, and that's going to give you an error at this particular point. A val cannot be reassigned. So tuples typically are immutable. That's a characteristic of a tuple, if you will. So, okay, that's great. But of course, as you know, Java doesn't have tuples. Well, yes, that would be great if Java has tuples, but in the interim, you may try something a little different, if you will. For example, you can create a record called names where you have a string, maybe a name 1 and a name 2, if you will. So that becomes a little way to create a tuple. So you could say names is equal to names. In this case, we got our friend Tom again and Jerry over here. And of course, I can output right here the value that I want to output is, of course, the names. So we could simply say names and print it. So even though records are a lot more than tuples, we could try to use a record, if you will, to create our own homegrown tuples. And as you know, tuples are immutable, and so are records. So you can do it that way, or you can come here and say dot name one, and similarly you can access name two as well. So you can access those data. So that kind of comes close to what you can do in Java with the records. So we talked about tuples, and I do have to say, that I really, really like tuples, one of my favorite concepts in programming. So we saw how we can benefit from tuples, and we saw a few examples in different languages as well. Well, the next thing I want to talk about here is one other thing I try to follow quite often when it comes to programming, which is to favor expression over statements. I do have to say I'm not a fan of statements at all, because statements often lead to mutability in code. On the other hand, expressions are easier to compose, and they avoid unnecessary mutability. So when I look at languages, I often ask the question, how much do the languages support expressions? As it turns out, functional programming languages are full of expressions and hardly any statement. If you look at language like Kotlin, even a print line returns a unit to emphasize that it's not a void function. It can be used as an expression. So expressions return values, whereas statements don't. And languages that promote expressions try to treat everything as expression, or as much as possible as expression as they can. Let's enter into this thought a little bit here in Haskell. So I want to go back to this Haskell code, and in here I want to say that define age is equal to, let's say a value of 20. Now I want to say let message is equal to, but notice if age is greater than 17, then I'm going to say then let's say adult, and otherwise I'm going to say else will say minor. So in this case, I use if as an expression rather than a statement. So if I try to print the message like so, what I expect to see in this case is a result of course, in this case, the adult, because age is greater than 20 or 17 rather, and you can see adult being printed. Languages like Groovy, Kotlin, and Scala treat if as an expression rather than as a statement, whereas languages like Java treat if as a statement. As you know, in Java, switch used to be a statement. Now switch is also an expression. So we can benefit from more expressions because expressions are better than statements for a lot of things. But let's entertain this thought here in Kotlin just for a minute. So here in Kotlin, I'm going to define age, another again, is equal to 20, but I'm going to say val result is equal to, and if age is greater than 17, I want to say adult, otherwise I'm going to simply say else, a minor. Again, notice how we are treating the function if as a expression rather than as a statement, if you will. So when I run the code again, you can see in the case of Kotlin, the result of this call is adult being printed. And that's basically an example of how we can use if as an expression rather than as a statement. Now let's think about this a little bit. When designing our own APIs, as an example, this is something that just blew my mind. For example, if I were to take an example of, let's say, things like Ruby, I can say class A, and I can end the class, and notice it says nil, just to emphasize that even the word class was actually an expression. So you can actually do something like this, foo equal to class A, and end like so. And you can define a foo as a variable that was assigned from a class. So class is not a statement, it's an expression. So that kind of illustrates the point that when languages are trying to treat things as expressions rather than statements. We can take that for our own code and start treating what we want to do as an expression rather than a statement. That gives us quite a bit of power on our hands, if you will. Well, likewise, we can enjoy curry. No, I'm not talking about my favorite Indian spicy dish. Currying is a concept where we can nicely reuse functions by caching parameters, if you will. So I'm going to give you a little example of how we can benefit from that in here in terms of what currying actually provides for us. But I'm going to show this in the REPL for the case of Haskell, if you will. So let's go over to the REPL again. And in the REPL, I'm going to say, again, set the type here so we can get a glimpse of what we are dealing with. Let add is equal to, let's say AB is equal to A plus B. Did you notice the syntax here? It says A arrow, A arrow, A. What in the world does it mean? Well, Haskell says a function can only take one parameter at a time. So even though you wrote add taking two parameters, internally it converted as a function that takes one parameter and returns, now look at the remaining part here, returns a function that takes one parameter and returns a result. So a function that takes one parameter and returns in turn a function that takes one parameter and returns a result. So in Haskell internally, functions only take one parameter. A concept of currying is implemented under the hood. Just out of curiosity, if you say let add ABC equal to A plus B plus C, as you would imagine, what is this going to be? Well, let's ask for the type of add, and notice this is A taking input, returning a function, which in turn takes an input, and returning a function, which in turn takes an input and returns a value, a function that returns a function that returns a function, where each one of them take only one value, as you can see. That concept of currying is extremely helpful to write some code in a very elegant form. Just to give you an example of this, let's go to Groovy here. I say add is equal to, let's take an integer A and an integer B and return maybe A plus B. So now that I've written that, I want to print out add of 1 and 2 here. And when I run the code, the result is a 3, as you would expect here in Groovy. However, I'm going to say define add 2 is equal to, and I take add and curry a value of 2. Now I print add 2, but this time I'm going to pass only a 3. And of course, 2 plus 3 is a 5. That currying has happened to take that data and say, I noted the first argument. Now I return a function that takes one argument and returns a result using the previously passed argument. That becomes a nice way to really curry things around, if you will. Some languages even call this as partially applied functions, where we are trying to really take the parameter and we are trying to cache them. So technically, you could say currying is a little bit deeper than that, but that's basically how we can benefit by reusing functions in effect. We can use that in our own code as well in languages like Java, if you will. For example, let me show you a quick example here in Java, just to illustrate the point. Suppose I were to say over here, a var numbers is equal to list of, let's say, a 1, 2, 3, 4, 5, and 6. Let's start with this. I can say here numbers dot, let's say, stream, and I can then say over here, for instance, I can say that I want to really take a filter, but I call it check.apply, and I'm going to pass a value of 5 to it, dot for each, let's say a system.out and print line. I want to simply print the result over here. So in this example, what does the check function actually provide, you may ask? Well, let's bring in a function like so, and I'm going to say this is going to be a function that takes an integer, and here comes the charm, returns a predicate of integer. So I can say check is actually taking a pivot, and then returning a function that takes an input and returns an input greater than pivot. So just like in the case of Haskell, notice the 2 arrows we are seeing in here, if you will, in this particular code, how powerful that is in the case of Java. So much like the example we saw in the case of Haskell, you can see one arrow followed by another arrow, just like we saw in the case of Haskell, where we said, if you want to look at the type of this, you can see that it's an arrow and an arrow, a very similar idea in the case of Java, where we are saying it's a function that takes an argument and returns another argument. Well, I'm going to cover a few things quite quickly in here. It really is useful to be lazy. And this is a concept that's beautiful in the case of Haskell, because Haskell is a language built around laziness, if you will. So as a result, in the case of Haskell, I want to illustrate a little quick example here to illustrate the laziness. So for example, if I were to go back to the Haskell code right now, I'm going to go ahead and write a function here called compute, where actually it's write an add function, AB is equal to A plus B. Evaluate takes a value, returns a value. Finally, I say a print, and the print function is going to take an evaluate. Let's fix the spelling here, evaluate. So the evaluate function, if you will, is going to take a value of, well, in this case, add 1, 2, and return the result from that particular call. So the result of this is a 3, as you expect. But just to illustrate the point, I'm going to prove the obvious here. So going into GHCI again, I can load the sample.hs right now. So let's bring up that file. Then I say put a breakpoint on line number 1, and I call the main function. You can see it's waiting on line number 1, and I say continue to produce the result at this point right here. You can see the result of the call is a 3. However, if I go back to the code and say value is going to be ignored and simply return the 42, well, Haskell uses what's called normal order. And as a result, in this case, if you will notice that in here, when I run the code again, go to GHCI again, and load up the sample.hs. And in this case, what you're going to notice here is that if I were to put a breakpoint on line 116 and call the main function, it never paused on the add function. That is because it is normal order. It is not going to evaluate add unless it's absolutely needed. Well, we can apply similar concepts in languages like C# and Scala and Kotlin by using lazy. Even though Java doesn't have it, Project Lombok has an opportunity for you to use it in Java as well. You can explore some of those concepts. And in the next couple of minutes, really quickly, I want to say that lambdas don't have to be noisy. So for example, in the case of, Haskell, I can say here is let numbers, let's say, is equal to, let's say 1, 2, 3, or 1 to 6. Let's go ahead and take those values. But I can say in here something like a filter, and I can then ask it to bring in maybe an element. And what am I going to ask it to do with the element in here? Well, I could ask it to, for example, take the element and give me only the even numbers in this collection. So you could say even of E. And then, of course, I could ask for the numbers to be evaluated like so. So this is going to give me only the even numbers in this collection. But I don't have to work this hard. I can instead simply say filter and pass the even directly as a function. So the model of the story here is when I program in Java, I try to use the same notion as much as possible, prefer method references over lambda expressions. And if you do have to write lambdas, definitely avoid multi-line lambdas. That's a lesson Haskell taught me. Just because I'm using lambda doesn't mean my code has to be ugly. I can make it so elegant that I could actually do away with lambdas and pass method references where possible. And the last thing I'll mention here is that you can reach for infinity by having infinite sequences. This becomes a very powerful idea you can use in Java using stream.iterate, but the concept is very similar to what you can do in Haskell. For example, I can say let numbers is equal to, and let's say 1 and a map of plus, but I'm going to say numbers. And how does this really feel? So I can say print, take only 5 from the numbers and give me the value. And you can see that it's going to get us only 5 numbers from this collection, if you will, that I can get those values very easily in this particular example. So this is another example of where we can use a very powerful idea. So this is going to be a +1 rather. That's what I want to add. And you can see that collection of 1 through 5 being printed here. We can use the same concept, as you know, in languages like Java as well. For example, if you're programming in Java, you could do something similar to that in Java, as you know. For example, I'll end with this example really quickly. So in Java, for example, if you have a stream, you can do something along the lines of, for example, you can say stream.iterate, and you can start with the number 43, and you can say given an element +1, and you can do a dot, let's say filter, and you can say given an element mod 2 is equal to 0, or write that as a method reference, writing a method, map to int given an element, you can say element times 2, and then finally you can say a limit, which is like your take function, and you can perform a sum operation, and infinite sequence you can enjoy in a language like Java as well. That really comes from infinite sequences. Just to note down, infinite sequences are really based on lazy evaluation, and correctness of lazy evaluation is based on immutability. And that is something that language like Haskell greatly enforces. When it comes to language like Java, we have to honor that. So I hope that this was useful. I kind of took some lessons I learned from Haskell over the years, and how I applied that in other languages. As I pick up other languages and even the mainstream languages, we can see some of those ideas, trickling in, and we can benefit from them as well. So in general, learning different languages has really made me at least a better explorer in the languages that I program predominantly, and I work with my clients in mainstream languages. We're able to apply better ideas in it as well. Thank you again for joining. I hope that was useful. Take good care.